Hello there. And in this video we're going to talk about another method that can be used for conducting a hypothesis test for the population mean. In the last couple of videos we talked about two methods, the first being a confidence interval, which is usually the most intuitive one for both people who know statistics and people who don't. And then the second method, which is sometimes used as, say, a shortcut or a quick way of conducting a hypothesis test, is via the method of statistics. So if you don't know how the method of test statistics works, then I definitely suggest understanding that method before we move on to the third, since this method builds upon that. So let's quickly review test statistics, what they represent, and how to use them. So consider this picture that all of us should be pretty much familiar with, which corresponds to some symmetric level of confidence, and let us assume this distribution is a t-distribution with new degrees of freedom. So given some level of confidence, and if this is the t-distribution, then there exist these two numbers, t alpha over 2 and minus t alpha over 2, which we typically refer to as the critical values of the confidence interval. So this number here and this number here, this is what we call the critical values. Alright, so pretty much what this thing does is, okay, we have this null hypothesis mu is equal to something, and this this alternative, this two-sided alternative, that mu does not equal that claim that they say it is. So pretty much what we're going to do is, we're going to go out and collect a sample, and we're going to get these what we call test statistics, and there's two that are commonly used. So there's the z statistic, which is usually equal to the square root of n times x bar minus mu 0 divided by sigma. Here mu 0 corresponds to the claim that mu is for the null hypothesis, and the bottom is the standard deviation of the population. As most people know, the standard deviation or other parameters of the population usually is not known. So if sigma is unknown or the sample size is really small, then an alternative is using the test statistic for the t-distribution, which is equal to the square root of n times x bar minus mu 0 divided by s. Here again, mu 0 is the null hypothesis mean, and s is the standard deviation of the sample acquired. So what do we do with these test statistics? So let us assume that one of these, or the one that we use, is either bigger than the t alpha over 2 or less than the minus t alpha over 2. So let us assume that it's over here somewhere on our distribution. So if this value is significantly greater than the critical value t alpha over 2, and it could be on the left side as well, namely it could be somewhere over here, so it could be significantly less than the negative t alpha over 2 critical value, then we have evidence to support that the null hypothesis is false. Because pretty much what it means is the difference between our sample mean and the hypothesis mean is significantly large. That is what's forcing these test statistics to be large. So let's write that out. So if the absolute value of, let's say, the t statistic is significantly greater than the critical value t alpha over 2, then we're going to reject the null hypothesis that mu is equal to mu 0. And that's pretty much how you conduct hypothesis tests for test statistics. So let's build into this next topic of hypothesis testing. So again, let's consider the t-distribution with new degrees of freedom. And let us consider some level of confidence c. So the traditional picture. So if that is true, then there exist these numbers t alpha over 2 and minus t alpha over 2 that makes that true, if it's symmetrically distributed around the mean. Alright, so let's assume that we get this test statistic here. So let this be the t statistic. So if that is the t statistic for one person, and another person gets another test statistic, say this one, let's call that t stat 2. So it's very trivial to say that this one has stronger evidence, and this one has weaker evidence. But nonetheless, both of these are bigger than the critical value t alpha over 2. So for both of them, we're going to reject the null hypothesis that mu is equal to mu 0, but it would be preferred if we get this t stat 2 over this other t statistical value. And that goes for the opposite side of the spectrum as well. So if you get this negative t-stat value, if somebody gets something a little bit less than that statistical value, then this value is going to be a little bit more stronger than the green one mentioned here. So pretty much what are we getting at here? So let us assume we get these green values, and let us shade in the area that corresponds to all test statistics that are better or equal to the ones we get. So this area here, this green area here, and this area here, this area is what we call the p-value. So the p here corresponds to a probability, of course. So what is this p-value equal to? So let's give a formal definition for p-value. And sometimes we're going to abbreviate this by p-val, p-val. So a p-value is the probability of acquiring our test statistic or something better or stronger that is in favor of the alternative hypothesis. And that is pretty much what a p-value is. So let's work through a couple examples on how to actually calculate this p-value. But what do we really want here? Well, if we were to calculate and go back to this picture, so this green area corresponds to the p-value associated to the test statistic in green. But if we get the stronger test statistic here, then the corresponding shaded region in burgundy is quite less, right? So what do we usually want for a p-value? Well, we want the p-value. So we want p-val to be small if we seek to reject the null hypothesis. So pretty much, we want the test statistic to be large. This corresponds to a smaller p-value. All right, so let's work through a couple examples on how to actually go through this. All right, so example 1. So let us, and all of these goes towards this standard hypothesis test. I know I write it continuously, but it's possible that it could change. And let's assume that we want to work under a 99% confidence level. And let's state a couple assumptions here. Let's assume that sigma is known and n is large, just for safety. All right, so if that is the case, then we're going to use a z test statistic for a test statistic hypothesis test. All right, so that means we're going to have some associated picture that is going to be similar to the following. So here is our region of confidence. And we're going to have some, test statistic out here. We hope anyway, right? So there's our z test, and there's its opposite, its mirror image. So it could be negative, it could be positive, but in either case, that is going to be the opposite one. So this green region corresponds to the probability of getting something more in favor of what we want. And keep in mind here, this region outside of C, because this inside region is C, so this is alpha over 2 and alpha over 2, so this green region should be less, significantly small, but less than alpha. Alpha corresponds to the complement of C, so the green region definitely should be less than alpha. That's the goal here. So this p-value, our goal, is to make sure that that is less than alpha. And that's always going to be the goal for a p-value hypothesis test. All right, so let's work through a couple of assumptions here. Let us assume that we go out and get a sample, S, and the sample allows us to get a z test statistic of, let's say, 2.96. So let's assume this is our test statistic. So what is the probability of getting this or something better? Well, if that is our test statistic, so this is Z stat here, which is 2.96, its mirror image is going to be over here, 2.96. So any test statistic that is less than negative 2.96 or greater than positive 2.96 is going to be more in favor of rejection of the null hypothesis, in favor of our alternative. So again, if this is a Z statistic, then this is the normal distribution. So that means this p-value is going to be equal to the integral from minus infinity to negative 2.96 under our standard normal distribution, plus, so that means this integral corresponds to here, and then the integral from 2.96 to infinity under the same exact distribution. So this integral corresponds to this area here. And if you calculate this integral out, you're going to get that this is equal to 0.003 approximately. All right, so that is our p-value, and recall that since c is equal to 0.99, that means alpha is equal to 0.01. So these are the two values that you are going to compare to. So what do we see? Well, we have that the p-value, 0.003, is less than, and you can say it's significantly less than alpha, 0.01. So since this is true, then we're going to reject the null hypothesis. And that's pretty much how that goes. So let's work through a similar example. Let's assume that we're working with the same exact scenario. Namely, the claim is mu is equal to something. Two-sided alternative, mu does not equal to that number. And let us assume that we're going to work under a level of confidence of 0.98 instead. That will force alpha to be equal to 0.02. Let us assume that n is equal to 15 for some sample that we have. If that is true and sigma is unknown, then we can't use a Z test statistic. That means we need to use a T test statistic. So if n is equal to 15, that means the degrees of freedom is equal to 15 minus 1, which is 14. So under this level of confidence and this degrees of freedom, one should be able to find that the critical value T alpha over 2 is going to be equal to approximately negative 2 point. No. What would it be equal to? It doesn't matter. It doesn't matter, actually. Because that's if you want to do a test statistic test. All right, so what is our test statistic equal to? So t-stat. So t-stat is going to be equal to the square root of n times x bar minus mu 0 divided by the standard deviation of the sample. And let us assume that this value for our sample comes out to negative 2.4. This is what I wanted to say. So this is not a critical value, but this is a test statistic. So is this significantly small? Well, we can calculate the corresponding p-value for this. So negative 2.4 is here. That's the obtained test statistic. And its mirror image is going to be over here, 2.4. So the p-value is going to be equal to this area. Now, if you calculate this the corresponding critical value for this level of test, you should automatically see whether you should reject or fail to reject by comparing the two. But we're going to sort of ignore it for the time being. If you want to calculate it to sort of verify that conclusion, then you can. But this integral from minus infinity to minus 2.4 under t, plus the integral from 2.4 to infinity of the t distribution, is going to be our p-value. And you're going to see that that's going to be equal to 0.031. And since alpha is equal to 0.2, and this number is smaller than this p-value, then what do we do? So from here, we're going to, so since p-val is bigger than alpha, that means we're going to fail to reject the null hypothesis. And in the next video, we'll go through an example where we test all of the 3 methods for the same hypothesis test. So see you then.